Hi, and very welcome to this webinar. I'm Roland Axelsson. I'm the technical account manager at Intinor, taking care of a lot of our customers, also with support and technical things. And together with me is Peder, Boberg, who is our product owner. And we are going to talk today about high-end streaming encoding for broadcast. So it will be a little bit about technical things. First, this is a bit the agenda. We will give you some introduction first, and then we will talk a bit about bitrate guidelines, how different bitrates for different kind of content, and how different technical aspects of this will change the guidelines for bitrate. And this, we will also talk about different codecs. So if you're using AVC or HEVC, or also a little bit about new codecs coming up. And then we will talk about transferring the content over internet using redundant streaming, different ways of doing that. And all the time during this webinar, you're very welcome to send your questions. So we will look at the comments on YouTube. So whenever you have any questions, you send them to us. And then when we feel that we have some good questions, we will take a break and answer the questions. And if we have time in the end, of course, we will also answer some questions in the end of the webinar. So a little bit about the company we work for, Intinor. We do solid solutions for live broadcast, and we have been doing this since more than 20 years now. We are a private-owned company, and we are based in northern Sweden. So we do all the R&D, development, production in-house. We have shipped more than 2,200 units now, encoders, decoders, routers for live video over internet. And our vision is to create the best solution for high quality live video over the internet. One of the technique we developed for this is a point-to-point transport protocol. And this is a network bonding protocol we call Bifrost Reliable Transport. So with this protocol, you can combine Ethernet plus 4G, 5G, even satellite links, and use all the internet connections together to get robust connectivity over internet. The Bifrost protocol has error correction, both forward error correction and also ARQ, retransmission. We can do very low latency with this protocol. We have adaptive bitrate and resolution in case your internet connectivity is not good enough. We can also send redundant audio in case one of your connections fail, then audio is more important. And we can do cost management so that, for example, your SIM cards are more expensive than your Ethernet connection. Then the Ethernet connection will be used much more than the SIM cards. So this is just to give you a bit background of what the company has been developing. And to use this, we have developed products, encoders we call direct link, black ones. And they can, of course, send with the Bifrost protocol, but also with other protocols like SRT, RIST, RTMP. On the other side, we have a direct router, which is a bidirectional. You can have encoder and decoder, and also be a gateway. So you can receive MPEG-TS in one protocol, forward them in another protocol, and also encode and decode from SDI or NDI. So it is a multi-purpose tool for live streaming over internet. We also have a basic receiver we call direct receiver, which has IP stream input and SDI output. So now we will go into the actual topic, one of the topics of this meeting, and that is to talk about the bitrate. And we have been working a lot with different customers, sometimes sport, sometimes event, musical events, news, other things. And this is a question that we hear a lot. What is your recommendation? And also, of course, we are listening to what the customers are using and trying to understand. So it's not so easy. First of all, or there are many things. One can say that the content is very important. Are you sending just a static camera, for example, this webinar we are doing, or is it high movement, sport, even e-sport? And then, of course, the codec. We will talk a bit about H.264, HEVC, but it's also about the codec vendor. So not all codecs with H.264 has the same quality at the same bit rate. So it differs a bit between different codecs. It's of course also about the resolution. Are you doing 1080i, 1080p 50, or is it 4K? And if you're doing it in software, it's also about how much CPU resources do you have? Can we put some extra CPU resources to get even lower bitrate at the same quality? What is the color depth? 8-bit or 10-bit? What is the chroma? 420, 422? And one very important thing, what is the latency requirement? For example, if we are streaming to YouTube like this, then we can have a high latency. But if we are doing remote production of sport, we need a very low latency, maybe 500 milliseconds compared to 4 or 5 seconds if we send to YouTube. And that also affects the bitrate we need to have. So to start somewhere, we put together a baseline, and that would be for a sport content in 1080p 50, balanced latency. We say that around 10 megabit is a good thing if you send with H.264. And you have medium CPU performance mode. So this is more or less our standard that most our customers are using. If your content is very static, like this, you can reduce the bitrate by 30-50%, and it will still look good. So from 10 megabit, you may do 7 or 5 megabit. If your content has very high complexity, like e-sport, a lot of details, a lot of movements in the picture, then you should increase the bitrate by 30-50%. If looking at resolution, if you can reduce the resolution to 1080i or 1080p 30 for the web, which you can do, 1080p 30 is good for YouTube for a webinar like this, then you can reduce the bitrate by about 30%. If you want to send 4K, then we are talking about 100% at least increase in the bitrate. If your latency target is balanced, then we are at a 10 megabit. But if you can accept a long latency, like sending a webinar, then you can also decrease the bitrate by 50%. If you want to have a very low latency, then you have to increase the bitrate by 100%. You can, if you have a lot of CPU performance, CPU resources available, you can use more of that and decrease the bitrate. And this is if you want to optimize, for example, a streaming of esport, then we can use more CPU power to send a lower bitrate. If you don't have so much CPU resources available, if you want to send 8 cameras, for example, and your resources are limited, then you can increase the bitrate instead and get the same quality. And of course, also about the codec efficiency. We are using in our products X264, which is a really good codec. And with some other solutions, you may need at least 10 or 25% more bitrate for the same quality. A little bit about interlaced and progressive, because we get a lot of questions about this from our customers. And 1080i is a kind of a compromise. If you have some older equipment and you don't want to send so high bitrate on SDI, so 1080i is just 1.5 gigabit. It also has you can use less bitrate than 1080p 50. With 1080i, you still get 50 frames per second. So movement in some sport that has very quick movement is still smooth, but it's not as sharp as progressive. And 1080i is not always accepted for streaming. So if you send to a streaming platform, they may convert it to P, or somewhere sooner or later it has to be converted to progressive. So in my example, you can use 7 megabit instead of 10 megabit if you're doing 1080i. And if we compare that to progressive has a higher bitrate on SDI. You need to use more bitrate compared to 1080i, but you get 50 real frames per second, which looks better, especially if there is a detailed graphics content moving, or for example, this tennis ball will look better at 50 frames per second than 1080i. And that, of course, depends on the deinterlacing in the device that is receiving it. P50 progressive is good for both broadcast and streaming. So when some content is going to broadcast and at the same time it goes to social media, 1080p 50 is the format we recommend. But you will need a little higher bitrate compared to 1080i. So now Peder will talk a little bit about some other technologies in this field.
So I will talk a bit about different way of increasing the quality of live streams. There are a few different ways of doing this, and I will cover some of the technical topics that facilitates this, and also explain a bit what they actually mean. So probably a lot of you know about 8-bit versus 10-bit, but I'm gonna cover it anyway. So 8-bit is basically 16.7 million colors, which sounds a lot, but for modern broadcasting, that's sometimes not enough. I think we've all seen, for example, TV series at home. Watching a very black scene can sometimes feel like it's a different gradients of gray instead of being a complete black. Going up from 8-bit to 10-bit decreases this problem, since you have basically more colors to choose from. So as you see in this example image, you get smooth gradients between the colors instead of these choppy blocks. 10-bit is also the baseline requirement for doing HDR, which I will talk about in a second. And basically 10-bit is very crucial if you're going to do some advanced color grading in your post-production of the video. So going from 8-bit to 10-bit, what will that cost you bitrate-wise? So just looking at the technical aspect of it, which the image here shows, for raw video, going from 8-bit to 10-bit basically increases the amount of bits needed by 25%. But modern codecs like AVC and HEVC, different codec vendors do this very efficiently. So it will require more computing power if you're using 10-bit compared to 8-bit, since the encoders and decoders need to work harder. But you actually don't need that much more bitrate. There's not an exact answer to this, but we usually say that it's up to 10% additional bitrate. But depending on your codec and the vendor, you can actually use the same bitrate as before. You actually do need to test it yourselves to get the exact answer on this question. And moving on from 8 and 10-bit to SDR versus HDR, and this is basically a even more detailed color scope that is available for you. So it's both for increasing color, making colors more vibrant, but it also allows the lighter parts of the picture to be lighter and the darker scenes to be even darker, which is a way of mimicking how the eye actually works. A scene on a camera with bright lights and darkness is usually quite blurry, but if you are going around in everyday life and you have a bright light shining at you, that doesn't have the same effect. And HDR is somewhat of the same way, but for the camera and the screens to show you the video in that way. There are a bunch of different standards for HDR. There's Dolby Vision, there's HDR10, HDR10+, but what's most common for broadcast is HDR HLG, which is short for hybrid log gamma. And this is basically because it allows you to be backwards compatible with SDR monitors, which is crucial for a broadcast where you can't control what the end consumer is using to consume the video. And what does HDR cost from a bitrate perspective? Well, since HDR HLG is the go-to standard for broadcasting, it doesn't cost anything. It's just metadata that explains how the video has been captured and explains how it should be presented on a screen. So of course your cameras need to support this. They need to signal it to the encoder, who also needs to support this, who needs to send it to a decoder that needs to support this. But it doesn't cost any additional bandwidth. And just to iterate, the main benefit of HDR HLG is that it's backwards compatible with SDR, which is very important. And another thing on the same topic, 420 versus 422. RAW video has color and brightness information on each pixel. This is called 444. But there's a compression way to save data, to save bitrate, which basically mimics how our eyes work. So our eyes can see brightness or luma better than color, chroma, and that's why you can subsample video without losing too much color information. So if you look at the image below here, you can see that 444 has 8 different colors, 422 has 4 different colors, while 420 only has 2 different colors. And this is because the chroma subsampling is using 75% less color information on 420 than it does on 444. So the difference between 422 and 420 is 50%. And these additional colors are very important when you're working with color tuning, VFX, and just making the colors look more vibrant, basically. And looking at the bitrate cost for 422 versus 420, this actually requires more bitrate because it's more color data. So we usually say about 15 to 30%. It depends on what kind of content it is. But it's important that you increase the bitrate when going to 422, because if you try to compress the additional color data into a lower bitrate stream, that could actually make the video end up looking worse, especially during fast motion. So to summarize, comparing the baseline that Roland talked about previously in the middle versus the new target to the right. So going from 8-bit to 10-bit, up to 10% extra bitrate. Going from 420 to 422, 15 to 30% bitrate. And going from SDR to HDR doesn't cost you any additional bitrate. But what if you don't want to use additional bitrate? What if you're satisfied with the 10 bits that you're currently using? Then we recommend switching out the codec. So if you are on H.264, then you can go on to use HEVC, which basically reduces the bitrate 30 to 50% depending on the content and depending on what your scenario is. And to talk about our experiences with HEVC compared to AVC, it's a large quality improvement, especially in lower bit rates. and it doesn't really require more CPU for us than H.264 encoding. I'm not sure how familiar you are with VMAF, but that's a way of analyzing video frames, how they are interpreted by an end consumer. So the graph here actually shows one line for H.264 and one line for H.265. The x-axis is bitrate and the y-axis is the VMAF score, the higher the better. So if we look at H.264 in 10 megabit, that's actually equal to H.265 in 3 megabit. This is only for this example, but it's a large difference. And as you can see, the difference gets smaller and smaller the further up in bitrate we go. And if you have ever visited us on a trade show, you know that we always show hockey, and that's because it's easy to spot the difference in quality. And the thing that we show here is on the left is H.264 encoded in 3 megabit in ultra low latency, so 500 milliseconds glass to glass, compared to on the right side the same settings but with HEVC. And you can see there's clear pixelations on the left, while the image is much better than on the right. Of course, when you're doing hockey, you shouldn't use these settings, but this is just to exemplify how much better it looks in HEVC in lower latency in low bitrate. And just to talk about the future a bit as well, today H.264 is still the dominant factor when doing live broadcast. HEVC is gaining. I think it will probably be on the same level in just a few years, if not already this year. But tomorrow there is, or in a few years, there are new codecs coming. VVC is the next version of H.265 basically, so it's called H.266. It's basically built on the same ground, but a newer version, a new format. And there's also AV1, which is a royalty-free open source alternative. And both of these codecs are very promising. They offer better compression than both H.264 and H.265. But of course, migrating to these will also require your encoders and decoders to support this. You will need to know that the decoding device that you're sending to actually supports this. And it will be very interesting to see if VVC or AV1 will be the dominant factor in the upcoming years. It will probably be a bit different from one market to another. But there are at least two promising alternatives to the codecs of today. And with that, I'll leave over to Roland again to talk about streaming protocols.
Okay, so I also first want to remind you that if you have any questions, you can send it on the comment field in the YouTube stream. So please send questions if you have anything on the topics we have been talking about. So yes, I'm going to talk about transport protocol, because when you have encoded your stream in a good bitrate and with a good codec parameters, you also need to transport it over the internet. And for this, as I mentioned in the beginning, we have developed our own transport protocol, Bifrost. Bifrost is really good when sending from an Intinor encoder to an Intinor decoder. In this case, we can also do very low latency, very exact latency. We can synchronize more than one camera. We can do network bonding, which is important. So you can have a network redundancy for Bifrost. But the disadvantage of Bifrost is, of course, that you need to have our encoder and our decoder. So it's a bit similar to if you compare it with LiveView or TView. It's only our protocol for our product. But it is a point-to-point protocol. So to have interoperability with other vendors, we have implemented both SRT and RIST. So we are a member of the SRT Alliance. So we work very close with SRT, and develop all the features for SRT. We also a member of the RIST forum, and we improve RIST implementation. And the big difference between those two protocols is that SRT is much more used by more vendors today. RIST is probably a bit in the future, but it's still used, but it will become more and more used in the future. So the main part of this, for that reason, that I will talk about SRT. And so what is SRT? SRT is a royalty-free open source protocol for live streams. That's why so many people are using it. And it's, I would say it's much better than the other open source royalty-free codecs or transport protocols. It supports encryption. It supports error correction. It's developed by a company named Haivision. But it's supported by many vendors. So it means some kind of interoperability between different vendors. And as I mentioned, we are an SRT Alliance member, so we have products with SRT, and we also work with other SRT vendors to make sure that our products are compatible. That's what SRT plugged means. And then comes the questions, is SRT then, are all devices compatible with each other? Not really, because SRT is just a protocol to send data. It doesn't specify the content of the protocol. You can send different codecs, you can use different container formats. So it doesn't actually mean that if you have an SRT product and another SRT product, they can talk to each other. But it's mostly used for sending MPEG-TS. So if one product sends MPEG-TS, another product that can receive MPEG-TS should be able to receive it. So MPEG-TS is a standard, and you need to have an encoder and a maxer that supports MPEG-TS. But then comes the problem that some decoders are even more sensitive, and MPEG-TS is not enough. They also require DVB compatibility, which is a little bit more strict than MPEG-TS. And also, not all the decoders support different codecs. So, for example, you need to have a decoder that supports HEVC if you want to send HEVC. It doesn't matter if you use SRT on both sides. And not all decoders support 422 or 10-bit or 4K or, for example, Dolby Audio. So that's what we have been struggling a lot with. Our encoders should support DVB. Our decoders should support a lot of different formats so that our customers can receive a lot of different SRT streams from different partners. So yeah, that's what this slide is about. You should have an encoder that is DVB compatible, and you should have a decoder that is multi-format decoder. Because even if you know that today you only receive H.264, but maybe next 6 months you will need HEVC, or you have a partner who is sending you HEVC 10-bit streams. And then it's very good to have a decoder that can also support that. But then there is another limitation with SRT. There is no network bonding in SRT, and there is no network redundancy. So almost all SRT products can only send and receive using one internet connection. So this is how it usually looks when you connect two different SRT products. You have an internet connection here. You send the SRT streams over internet. You have an internet connection on the receiver side, and then you receive on that, and then you get SDI out on the decoder side. And this means that you have one path over internet and basically 3 different points of failure. So we have sometimes support with customers calling us and say, "Oh, I did a speed test on the sender side, and I have 300 megabit up. Why can I not send 10?" then the problem is probably either on the receiver side or somewhere between. So it's a bit risky to send over internet with just one stream. And SRT has something called path redundancy, but very few vendors support this. So it's a part of the SRT implementation. Yeah, I talked a little bit before here. So this is the 3 single point of failure. What you have, error correction solves minor packet loss, but congestion, I used to explain it as when you start testing something or you start sending, then everything works fine. But sometimes after a couple of hours, then the internet capacity reduces because many people are using internet, and there will be congestions. And there can, of course, also be interruptions, and this could be a technical problem with a network operator or a peering somewhere on the internet. So you have 3 single points of failure. And the solution to this is redundant SRT based on open standards. So this is a concept that was developed by Eurovision Services, EBU. And we work together with them, and they have a lot of live contents they want to send to partners all over the world. And they realize that when more and more partners receive SRT, then they have more and more problems, because sometimes they have internet issue, not always Eurovision Services, but some of the takers or some peering over long distance internet. So this concept is about your MPEG-TS, and then you put RTP on top of that. SRT is just a transport protocol, so you can send RTP streams over SRT. And then there is a standard called SMPTE 2022-7 to do seamless content switching on the receiver side. So you will receive 2 or more streams, and it can make sure that your stream is working when all the packets are received. So yeah, RTP is only, it's called real-time transport protocol. It's an old protocol that has been around for many, many years. It runs on top of UDP. It doesn't have any error correction, but that is in the SRT layer. So, but what RTP does, that it adds a header with a sequence number and a timestamp, so that a receiver can know how many packets were lost. All the packets get a sequence number, and it can know when it was sent, so it knows when to put it into a buffer. SMPT 2022-7 is also a standard for protection switching between RTP streams. So 2022-7 requires RTP, and that's why RTP is used here. So if you combine those building blocks, you can actually do redundancy in different ways. You can have 2 different internet connections, and you can send 2 SRT streams from one encoder. So then you get redundancy over 2 internet connections. But you can also get redundancy between RTP over fiber and SRT stream over internet. And you can get redundancy between RTP over satellite and internet connection using SRT. So compared to the path redundancy in SRT, this concept covers more use cases, which is very, very useful. And this is how it can look. This is the concept recommended by Eurovision Services when they send content, and it's compatible with different vendors. So any vendor can implement this because it's open standards. So on the encoder side, you can have STI or MPEG-TS input, and then 2 RTP streams are created and sent over SRT with 2 different internet providers. On the receiving side, you can also have 2 internet providers, and then the seamless redundancy switching will make sure that you get a good SDI out or MPTS out even if any of those internet connections fail. And even if you don't have two ISPs on the receiver side, for example, it's better to send over two different ISPs on the sender side, or the other way around. So some redundancy is always better than no redundancy. So you can reduce the number of single points of failure. Also important when you're sending with SRT and redundant SRT is management. If you cannot control in a good way the encoder and the decoder, if you cannot manage those, it will be very difficult to see if something is working, if something has to be changed, some settings or something. So make sure you have a way to monitor and remote control your equipment. And also, if you do have some problem, make sure that you have a reseller or a vendor you can talk to, so that you can get some answers to your questions. It's also good to think about a flexible device that you know what you want to do now, but if you invest in a basic decoder that can only take IP stream inputs and SDI out, and then in your next project you want to have something more advanced. Maybe you want to have also inputs, or you want to have something bidirectional, or you want to have a gateway. Good to think about when you buy equipment. So our key takeaways from this is that if you want to send something with higher quality, it means that you have to increase the bit rate. So if you have a 10-bit 422, if your content is moving very fast, you should increase the bit rate. Unless you can use a new codec. So if you can go from H.264 to HEVC or even to AV1, then you can reduce your bitrate again. Sending video over internet can be very robust, even more robust compared to a single fiber or a single satellite. So using internet is a very cost-efficient way of sending content, but if you don't use redundancy, then it's also a risky way. If you use redundancy, then it's a safe way to send video over internet. If you have a network bonding protocol like Bifrost, you can also use 4G and 5G for your redundancy. But if you want to have interoperability with other products from different vendors, then redundant SRT is the best choice for as a protocol today. Didn't we have any questions during the session?
No, actually, we haven't had any questions during the session. But of course, feel free to send them our way after the webinar if you have any questions. And the webinar will also be available to watch at a later stage on YouTube as well.
Thank you very much for watching, and hope you will be in contact with us to learn more about this. And I can also mention that we will probably do a few more webinars in this series. We are working on 2110 at the moment, so when we have the products ready for 2110, we will probably do a webinar similar to this to explain what the advantages and disadvantages of using 2110 in a broadcast environment. Thank you very much for watching.
Thank you.